Good afternoon, everyone. It's great seeing all of you here in Indianapolis for this year's North American Cystic Fibrosis Conference. I'm really excited. Because you're going to hear a lot of amazing progress being made, but I'm also excited because the history of this conference is that it has been effective in accelerating our mission. And as I look out over this huge gathering, I cannot even see the end of the room, I don't think. I have great hopes for this year. So welcome, we're thrilled you're here. I also want to welcome those of you who are joining us online. We're glad you're here. Can you all give them a hand? Let's make them feel welcome. Thank you for joining us. So the amazing progress made in cystic fibrosis over the decades has been enabled by collaboration. People working together, people sharing ideas and data, and that's been you all. Caregivers, scientists, industry representatives, volunteers, CF Foundation staff, and most importantly, people with CF and their families. You are responsible for the amazing story that you're going to hear today, so thank you. Now, in that recognition, what's often forgotten is the contributions and efforts of the CF Foundation's Board of Trustees. And I'll tell you, we have a very talented board, and it's now my privilege, not quite yet, Cam, but it's now my privilege to introduce its chair, Cam McLeod. Cam, in her tenure, has overseen rather significant change and progress in the CF field. She takes credit for nothing, and most of you don't have any idea how hard she or the rest of the board works, but they've all been very critical to our success. So now, Cam, let me please welcome our remarkable board chair, Cam McLeod.
Thank you, Preston. I am so thrilled to welcome all of you, nearly 5,000 this year from around the world, to the 31st North American Cystic Fibrosis Conference. It's an honor to be here with you with this special group, including many of my fellow board members. It is unquestionably a time of great momentum in our journey to cure CF. Every day, whether working in the lab or the clinic, or raising funds and awareness, you share your talents and help move our mission forward. Thank you from the bottom of my heart for your hard work and dedication, and for your ongoing commitment to working together to help people with CF live healthier and longer lives. I'm delighted to see the team from Indianapolis office here, and also an extraordinary group of dedicated volunteers from this region and beyond. Thank you for your tireless efforts, which make our exciting progress possible. Please join me in thanking these wonderful volunteers here at the front. I'd also like to welcome a dear friend of many of ours, Dr. Robert Bell, former president and CEO of the Cystic Fibrosis Foundation. Bob, thank you for your years of extraordinary vision and dedication, which has helped to bring us to where we are today. Thank you so much, Bob. And as Preston said, I'm thrilled that today we're also joined online by many friends from our CF family, especially those of you with CF. You inspire all of us in this room to continually look at CF and CF care and research in innovative new ways. You are the heart of all that we do. I'm looking forward to being here with all of you, learning more over the next few days about the latest medical innovations and scientific breakthroughs in CF. Together, the work that you're doing now is bringing hope to every person living with CF and those who love them. I'd like to share a few words from friends in our community about what your important work means in their lives. We regularly hear from people on Twitter, Facebook, Instagram, you name it. And our community is full of thanks for you. Now, please see the thank yous. And there are a few that I would like to personally share with you. The first is from a mother of a child with CF. Isn't she beautiful? When you have a child with CF, you have a whole new life presented to you. So it's really important to find people who are going to be part of that new life and support you. The members of our care team are those people to us. And here's another one from a young man with CF. Researchers are the unsung heroes, the engine that pushes us toward the finish line. Cystic fibrosis is no longer a childhood disease, and so much of this accomplishment is a direct result of their hard work and dedication. From a personal standpoint, I would like to share with you that this plenary session is of particular significance to me. As many of you know, my own son Will had cystic fibrosis. He had 2 rare CF mutations and was among those who didn't have a treatment for the underlying cause of his disease. He was in that last 5%. Will is not here to benefit from the many exciting developments in the pipeline, but I know that he would be so encouraged by the optimism in our community as we look on the horizon and see a new future for every person living with CF. Because of your inspiring commitment, I am staying in the fight until the end, like so many other families. We all want a cure for all people with CF. We're so fortunate to have you by our side, the best in the scientific and clinical worlds, the most dedicated friends and supporters, and our unselfish, united, so unique community. Thank you all for being here, and I wish you a very wonderful conference.
Cam, thank you for that welcome, and thank you for what you're doing to help us complete our mission. Hey, I'd like to congratulate all of you on another remarkable year of progress. The CF story continues to be the most amazing story in medicine today, and I want to share 2 areas. I had a whole lot of things that I could share, but I'm going to choose 2 that highlight our progress over the first year. The first is a measure of how we're doing, and to do that, I'm going to use the median predicted survival number that's calculated from the patient registry data. And we're pleased over the years, both in the US and worldwide, that the median predicted survival has gone up almost year after year for people with CF. But this year in the US, it really jumped. And I want to share that with you because I think you deserve to know it. Last year's median predicted survival was 41 years. This year, that number jumped to 47 years. Yeah, you should be applauding. 41 to 47, that's a significant jump and a meaningful number for people with CF, and we have to keep that trend going. The second area looks really into the future. And to look into the future, we're going to look at the exciting progress being made with CFTR modulators that are those therapies that address the basic defect in cystic fibrosis, the CF protein. Now, with help from all of you and really the entire CF community, Vertex, an important partner of ours since 1998, has had a number of recent very strong successes on this front. First, the FDA expanded the ivacaftor label, adding 28 mutations, meaning more people than ever before have access to this therapy. It also has implications that will be brought up later in this plenary. The phase 3 tezacaftor, ivacaftor trial data looks very promising, and the FDA will make a decision on the new drug application the first part of next year. Now, while this combination is similar in some ways to Orkambi, it has a more favorable side effect profile, and for me, more importantly, it combines or doses more easily with their next-gen correctors. And speaking of their next-gen correctors, in July, Vertex announced strongly positive results from 3 early phase trials using its next-gen correctors combined with tezacaftor and ivacaftor. Perhaps this was the most important significant jump in our success in 2017 and bodes very well for the future. Triple combination modulator therapy appears effective enough to not only treat individuals with 2 copies of F508del, but also treat those with 1 copy of F508del, meaning that almost 90% of people with CF, those who have a single or 2 copies of F508del, could potentially have approved, highly effective modulator therapies available by 2020. I want to drill down on those efficacy results just a little bit because the early trial results predict that individuals with 1 F508del will have efficacy benefits similar to those seen with ivacaftor treatment of G551D. So if you have 1 F508del, you're going to receive a benefit similar to that seen in G551D with ivacaftor. But if you have 2, it's going to be much better than that. That's important because we know from the registry data that individuals with G551D who are started on ivacaftor early in life don't have a median predicted survival of 40 years or even 50 years or 60 years. We expect them, because of their rate of lung function decline, to live through their 70s and 80s, and that's where we're going. By the way, this work came out of our second generation screening program, started 8 years ago. Bob remembers us starting that. We've committed over $200 million to that effort. Obviously, Vertex is further along, and we're very happy about that. But the second generation effort includes a number of other exciting industry partners, and you will be hearing from them for sure. Now, while we're excited, really excited about all these advances, I need to quickly add that we're not done. A few of you may be saying, well, Preston, wait a minute. 95% of people living into their 70s and 80s, surely that's good enough. Well, let me tell you, if you walk into the new CF Foundation offices in Bethesda, the first thing you're going to see on the wall is a statement, until it's done. Until it's done. What do we mean by that? Well, let me give you 3 things that we must do before it's done. And here's the first one. We will not stop until everyone, 100% of individuals with CF have CFTR modulators. We're not going to leave anyone behind. In today's plenary, you're going to hear about moving from 60 to 90, 95%. But to move from 95% to 100%, we're going to have to deal with mutations that don't even make a CFTR protein. So how are we going to do that? How are we possibly going to do that? We're going to do it by developing new therapies that address nonsense mutations, those mutations that don't read through. With that, success will be at 98%, and to get to 100%, we're going to develop mutation-agnostic therapies, messenger RNA or DNA that will enable the production of a normal CFTR protein and get us to 100%. But look, even if when we get to 100%, we're not done. And that brings me to the second thing we must do. People with more advanced disease today are going to need more than just CFTR modulation to live long, full, productive lives. They're going to need novel antibiotics that treat multi-drug resistant organisms such as Pseudomonas, B. cepacia, MRSA, non-tuberculous mycobacteria. They're going to need novel anti-inflammatory drugs. They're going to need mucolytic drugs and more. That's why we're working with 48 antimicrobial programs, 17 anti-inflammatory programs, and 4 mucolytic programs to bring these therapies to these people. But it's not just new therapies. Some people's lung disease is so advanced that they're ultimately going to need lung transplantation. Approximately 200 individuals with CF each year in the United States will undergo lung transplantation. Wouldn't it be great? Wouldn't it be great if we could significantly increase the survival after lung transplantation? Double it, or maybe even more. That was the genesis of the Foundation's lung transplant program that began a couple of years ago, and we're very, very happy that Dr. Alfaro at the Foundation is leading that, along with Joe Paluski at Pittsburgh. And guess what? You're going to hear more about that in the second plenary tomorrow morning, and you should be excited about that. I'm going to rush back to new therapies just for a second. All the great work that Drs. Bill Skatch and Mike Boyle and their teams are doing to bring new therapies forward has created a pretty remarkable increase in the number of clinical trials. The number of trials in the U.S. in the past 5 years has more than doubled. 26 trials to 56 trials, demanding that we increase our funding from $11 to $22 million for the clinical trial network. And we don't stop there, we're also funding clinical trial networks outside of the United States to make sure that we can get these trials done efficiently and safely. But there's another issue besides building capacity, and that's keeping the community engaged. And I'm really excited about this, to keep the community engaged and aware of the need for these clinical trials in order for us to continue to move forward. Dr. Boyle and his team and the really fabulous communications team at the CF Foundation have built a soup to nuts program to do just that. And you can check that out at our booth downstairs or down the hall. But this video will give you a little bit of a flavor of where we're going with this. Check it out.
They call them trials, clinical trials, like they're hard to do, some heroic thing. Whoever named them trials hadn't met us, hadn't seen what we do, what we go through every day just to do what others take for granted. We don't complain. Whoever named them trials hadn't met our clinicians, doctors and nurses who chose working with 30,000 or so people scattered across the country. Whoever named them trials hadn't met our researchers, with us every step of the way. They'd like nothing better than to be out of a job just for our sake. Whoever named them trials just didn't get it. Clinical trials are the path, our path to a cure. Move one little letter and the whole picture changes. Raise one hand and you're blazing a trail. Join us, become a trailblazer, and help create the path to a cure.
Yeah, you clap for that. Congratulations to the team that has brought that forward. You know, all these, isn't that great? I just love that. So all these efforts that I've discussed so far are helping add tomorrows for people with CF, helping them to live longer. Equally critical is the work that's being done to help people with CF live better today. Dr. Bruce Marshall leads the effort to help care centers more effectively address the pressing needs of people with CF. This work has transformed care delivery thanks to so many of you in this room. And our funding for that is growing so rapidly has also doubled in the last 4 years, enabling a number of new programs, including the very important comprehensive mental health initiative that's already making a difference in the lives of people with CF. And likewise, our policy and advocacy group led by Mary Dwight is really second to none. It's been a really tumultuous year for those of you that don't live in the United States for healthcare reform. And this group has been involved and has been up day and night fighting for people with CF so that they will have access to the life-saving therapies that they're going to need not only tomorrow but for years to come. But you know, it's not only that they're doing. Give them a hand. They do so much more, and it always surprises me when someone doesn't understand the great work that Compass is doing. Please check out our booth to learn more about that. But they're helping people navigate their very complex health insurance needs and helping them find assistance for things that no one else offers. So it's an amazing service. And likewise, Dr. Drusy Borowitz, who's also joined the foundation, in a very short period of time has formed a very strong community partnerships program. That program has been charged with listening to the community and then based on what they hear, developing programs that meet the needs with people with CF so that they can live better today. And guess what? The third plenary is going to highlight this work and the policy and advocacy work. So you want to make sure that you certainly don't miss that. But let me just end by saying this. Even when 100% of people with CF have CFTR modulators, and they have all the therapies that they need to live long, full, productive lives, and all the programs to help them live better tomorrows, we're still not done, which brings me to the third thing that we must do. Our mission is to cure cystic fibrosis. And the very exciting science of gene editing now allows us to dream and plan for that day. It's a moonshot for sure, and it'll take a long time, but our dream is that these treatments that we're working on now will one day allow someone to say, I used to have CF. I think that's remarkable. How cool would that be? Then we're done. But what may not be clear to all of you is how we're racing forward and how much all of this work has been accelerated. For example, last year we met with over 130 companies. I can remember when we'd meet with a handful every year. In 2012, we funded 6 industry programs, and there was a lot of exciting work being done. This year, we're going to fund more than 39 industry programs. Think about that. That's essentially a 7-fold increase. We're very excited about that. Not surprisingly, the medical scientific budget has increased from $87 million in 2012, $87 million to $180 million this year. During the same time, Bill and his group have issued research grants increasing from 2012 from 500 to 1,200 last year. I could go on and on and on, but hopefully you get the picture. With your help, we're racing to a cure for all people with cystic fibrosis. So thank you so much for being here. Thank you for all that you do to make a difference. Enjoy the plenary and enjoy this conference. Thank you so much. And I have the pleasure of introducing my colleague, Dr. Bill Skatch, our Senior Vice President of Research Affairs. I have the honor of working with some really amazing people at the CF Foundation. In Bill's role, he's charged with our research and drug discovery effort. And I'll just end my introduction of him by saying we could not be in better hands.
Thank you, Preston. Good afternoon. I'm really delighted to be here with all of you today to open up today's plenary session. This is really one of my favorite sessions because it highlights some of the most exciting scientific discoveries and priorities that we have in the CF field. And as we have just heard from Preston, we are truly in the midst of an amazing transition in the CF world where new scientific and clinical advances are coming forward almost every week. But before we begin the presentation, I would like to take a few moments to recognize some very important people. First, our Program Planning Committee, shown on the slide here. This group of individuals works all year long, starting in January, to put together this program. They put in a tremendous amount of time and energy to choose the topics, develop the workshops and symposia, and then work with the speakers to make sure that you all hear the most exciting and up-to-date information. In appreciation and dedication of all the people on the committee and all their work to make this North American Conference a truly exceptional conference, I ask all the committee members to please stand so that we can recognize and thank them for all their work. I would also like to extend our sincere gratitude to this year's co-chairs, Professor Stuart Elborn and Peter Greenberg, for their long-standing leadership and exceptional contributions to CF. Dr. Elborn is an internationally recognized expert in CF care and clinical research at the Brompton Hospital, the Royal Brompton Hospital in London, and we are particularly pleased to have him as co-chair to recognize his work in helping foster the many international contributions that help make this conference a success. Dr. Pete Greenberg is a world-renowned laboratory scientist and a pioneer in the field of biofilms. And his work has really transformed our understanding of how infections affect the CF lung and how we can best treat those infections. Peter, Stuart, thank you for all you do, and please come to join me on the stage to receive a small token of our appreciation. We are also grateful to many sponsoring organizations and exhibitors for their generosity to help support this meeting. This year, support from our sponsors is greater than ever, and it really reflects the diversity of partnerships and collaborations that have helped make CF such an exciting story. Please take a moment to meet with and personally thank the sponsors as you walk through the exhibit hall. My last task before beginning the talk for the speakers is to announce the recipient of the Paul de Saint-Ignace Distinguished Scientific Achievement Award. Now this is the highest research recognition that is given by the CF Foundation, and we don't award this to every year, but we choose very specific years when there's been a truly exceptional achievement that has had a major impact in our mission. And in presenting this award, it is my pleasure and privilege to introduce and discuss one of the great leaders who revolutionized our understanding of CF. Paul de Saint-Ignace was an outstanding teacher, clinician, and mentor that had a huge impact in everything we do today. But his legacy to us here and the entire CF community is really linked to his scientific advancements. In the 1940s, Dr. de Saint-Ignace was a young pediatric pathologist at Columbia Presbyterian Medical School. And there he cared for children that were afflicted with a very newly diagnosed disease called cystic fibrosis of the pancreas. At that time, little was known about that disease. And his research revealed very key information on the effects of the disease in the lung and the use of antibiotics to treat those infections. In addition, his studies on sweat electrolytes were fundamental and paved the way for the sweat test that we still use today, provided clinical advances that helped our understanding of the underlying chloride transport defect, and really have helped shape the way we've approached this disease over the last 60 years. Today we remember this incredible scientist and clinician by presenting the Paul de Saint-Ignace Distinguished Scientific Achievement Award to Drs. Phil Thomas, professor in the Department of Physiology at the University of Texas Southwestern Medical Center, and Dr. Gary Lukash, professor in the Department of Physiology at McGill University in Montreal. Not just yet, Phil, not just yet. I've known Phil and Gergely for about 30 years when we were postdocs together, just getting started in CF. And it has really been amazing to follow their contributions over this entire time. Phil and Gergely, like many of my generation, started working on CF in 1989 or 1990, about the time the gene was cloned. And what they've really done over the last 30 years is to work on understanding how mutations in the CFTR gene impact the function of the CFTR protein. Now, one might think that that's a fairly simple task, but I think we can all agree that it's taken them quite a while to get this figured out, and they're not done yet. Phil received his bachelor's degree in chemical engineering at Columbia University, his PhD degree in biochemistry at the University of South Dakota, and he did his postdoctoral research work in biophysics at Johns Hopkins University. And it was there that he started looking at how the F508del mutation impacted the structure and folding of CFTR. Gergely received his MD and PhD degrees at Semmelweis University, Semmelweis Medical School in Budapest, Hungary. Then he moved to the States and did his postdoctoral work in physiology and pharmacology at Yale, and then moved to Toronto in the Department of Physiology, where he subsequently made a series of very elaborate and detailed discoveries about how the mutant CFTR protein is recognized in the cell. But it was about 2005 to 2007 when Phil and Gergely were recruited, basically, by Bob Bell and Preston Campbell as founding members of a consortium of scientists who were given this simple task of figuring out how to solve the folding problem of F508del. And I can still kind of hear Bob's voice, which was, find out what's broken and fix it. This isn't rocket science. And I can recall the early conversations sitting around that room saying, wait a minute, no one has done this before. It's totally unprecedented, and we're not even sure that it's possible. At the time, though, there were several screening programs that had begun to identify corrector molecules that improved CFTR folding. And the problem was that none of these molecules came even close to restoring normal CFTR function. So working closely with the consortium and members of the scientific community, Phil and Gergely developed a genetic screen, a genetic approach, to systematically add back mutations into CFTR that would correct the F508del defect. And by evaluating a whole series of mutations in different parts of CFTR, they showed, starting in about 2009, 2010, that it was possible to turn the mutant protein into an almost normally functioning protein. They identified two specific defects. They identified where on the protein those defects existed, and they showed that if you put both of those corrections back, you could get enormous function of the protein. This two-head hypothesis that came out of that work really dovetailed very nicely with work that Martin Mensa was doing, combining different corrector molecules. And over the last 10 years, these findings have had a huge impact in helping setting the stage for the next generation of modulators. And as Preston mentioned just a moment ago, we are just beginning to see this discovery in action. The first clinical results of triple combination modulators, where two correctors work cooperatively, in combination with a potentiator, restore remarkable levels of CFTR function, an activity that we expect will provide effective therapy for more than 90% of people with CF. I can only say that as I've watched this story unfold from the basic research experiments in the laboratory all the way to the clinic, it has been a truly remarkable process. And it really shows that what we as a united community can do by working together to solve problems that once seemed nearly impossible. Please join me in congratulating Professors Gergi Lukács and Phil Thomas as they come to the stage to accept this well-deserved award. Okay, so finally, it's now time for me to introduce today's plenary speakers and the presentation entitled Matching Mutations with Medicines. During today's plenary, you will hear how the CF community is leading the way in personalized medicine so that more and more people can benefit from existing medications, including some people whose mutations are so rare that it's impossible to do standard clinical trials. Our first speaker is Dr. Mike Boyle, who is known to many of you. He's the Senior Vice President of Therapeutics Development at the CF Foundation and a Professor of Medicine at the Johns Hopkins University Medical Center. Mike oversees the clinical development programs for new therapeutics at the Foundation, and he also is in charge of the Therapeutics Development Network, which is now 89 centers strong and really runs virtually all of the multi-center clinical trials in the U.S. He's internationally known for his clinical research in both CFTR modulators and difficult-to-treat infections, and for his work to improve the care and health of CF adults. He has been involved in CF research for more than 20 years, including founding the Johns Hopkins Adult CF Care Center, which has become one of the largest programs in the largest adult centers in the United States. He was the principal investigator of the international CFTR modulator trials, including the phase 2 and phase 3 trials that led to the approval of Orkambi. Throughout his career, Mike has made many contributions to the development of new drugs to treat cystic fibrosis, and today he will tell us about the very exciting clinical advances that have occurred just in 2017 and how they will impact approval for drugs in the future. Our second speaker is Phil Thomas, whom you just heard a little bit about. As I mentioned, Phil has really dedicated his career to understanding CFTR folding and the CFTR protein, but what I did not tell you is that once the CFTR modulators for F508del were really on track and moving forward, Phil turned his attention to start investigating rare mutations and how rare mutations affect CFTR folding. And in this area, he's really been an early leader in showing that CFTR modulators that we think about for F508del and G551D also work on other mutations. This concept has been called theratyping, and you'll hear more about that in the plenary. It's already having an impact on the approval of modulators in CF, and we think that it opens an incredibly exciting possibility to rapidly extend these medications to everyone who might respond. I'm so very pleased to have Mike and Phil present today's plenary, and as Mike comes up to the stage, I would like to share with you a short video highlighting just how important theratyping is and the impact that it can have on changing people's lives. Thank you very much.
Let's see, here's the Ursodiol for your liver.
That's for the morning.
Don't you do one in the morning, one at night?
No, I do 2 in the morning.
Okay, how's school this week?
It was good.
My daughter, Haley, was diagnosed with cystic fibrosis when she was 2 weeks old. Haley's personality is kind of laid back, a lot of fun. She's very kind, caring, gentle-spirited. She's the one friend that everybody kind of likes to hang out with because she's just a good person.
My name is Callie. I was diagnosed with cystic fibrosis at the age of 5. My mutations are the Delta F508 and A455E. My friends would describe me as caring, strong, and compassionate. was in the hospital for, as they call, a tune-up. I got the call that I was approved for ivacaftor, and it's an indescribable feeling, but especially for me, because as my symptoms were increasing and they were symptoms that I had never had before, getting that text that I was going to be able to start ivacaftor was huge. I think one of the biggest changes that I actually noticed right away was an increase in energy level. I truly believe that's just because my lung capacity is getting better. I can take a lot deeper breaths than I was before in just the short time that I've been on it.
Hi, I'm Haley. I'm 12. Some of my biggest fears is having a surgery and then not having cystic fibrosis cured.
Haley's mutations are unique because they are more rare, so there's not enough people in a study to even do a study at this point in time.
If I were to get on a modulator, then it would help my shortness of breath. It'd make me feel like I could go run and I could go play with my friends. It'd make me feel good.
I think it's so important for this research to continue on these modulators to be approved for more mutations, because to know what it's done for me would be huge for other individuals that I know who struggle more to be able to have this amazing opportunity. Ready?
My hopes and dreams for Haley is that, one, she can live out on her own because she thinks she's going to live here forever. And I would really love to see her be a flight attendant, because I know that she wants to be able to travel the world and experience new things.
If they find a modular for me, I'd say thank you. Yeah.
If I was able to talk to any of the researchers or individuals who have been doing these studies, I think a big thank you would be probably the biggest thing, and just that I hope they truly understand what kind of impact they're having on people with cystic fibrosis.
Wow, what a video, huh? Good afternoon, everyone, and welcome to the first plenary. It's a real privilege to be able to speak to you today. And the title of our talk today is Matching Medicines to Mutations. And Phil Thomas and I are going to act as a tag team today. And I'm going to talk about the clinical part. Phil's going to talk about the basic science part. And you're going to see sort of how these two have interacted to really advance CF therapy in 2017. But I think the key thing is that the goal of our talk's pretty simple. Our goal is that by the end of these two talks, you'll realize that 2017 has been an absolutely amazing year for advancing CF therapy. As a matter of fact, someday we're going to look back at 2017 and we're going to say that it was the pivotal year where we went from hoping that someday CFTR modulators were going to change and transform CF to actually now fully expecting that CFTR modulators will transform CF within the next few years. And you'll appreciate that this has happened sort of in two different ways. Part of it's been through clinical trials, which I'll talk about. Part of it's been through the advances in basic science, which have opened new doors to evaluating and even approving modulators for more people with cystic fibrosis than ever before. People like Callie and eventually Haley, we hope. So I don't have any disclosures to make other than I'm really grateful to Genevieve, Ashton, and Stephanie for all their work, so thank you guys. Let's go in, and I think and really appreciate 2017. What we need to do is to actually think back this time last year, when basically we had 46% of people eligible for Lumacaftor, ivacaftor, or Cambi, and another 8% eligible for ivacaftor, right? But this unfortunately meant that there was 46% of people who were not eligible for a modulator. And this was actually a pretty diverse group. There was actually about 1,700 other mutations mixed into this group, all right? So if we were going to make a big difference in 2017, we had to do two things. One is we need better treatment for those people already on modulators, because we know Orkambi's been a great first step. But if we're going to really transform CF, we're going to need to actually have something much stronger. And we'd also need to be able to address, of course, those 46% of people without any modulators. So what have we done? Let's talk for a second before we dive in. Let's talk about that 46%, because I think it highlights really what the work that needed to be done in 2017. And you can actually divide the 46% into 4 groups. One of these groups was a group with residual function mutations. Remember, residual function mutations are those where the protein actually makes it up to the surface, but it doesn't really work correctly, or there's not quite enough of it. This is usually associated with a little bit more mild disease. Oftentimes these individuals don't have to take enzymes when they're younger. For people who are familiar with mutation classes, these are the class 4 and the class 5 mutations. But the thing is, we really thought that there was a good chance that this group could be treated by Kaleido. But we had insufficient amount of clinical or laboratory data to be able to get the FDA to say, yes, we agree, this group should benefit. So that was one group. Callie would be a perfect example of this. She said in the video that she was diagnosed at age 5. That's because her A455E mutation is a residual function mutation. But we were left with this thing of thinking that she might be able to benefit, but she was not able to benefit yet. The next big group is a group of individuals that have just a single F508del mutation. Remember, we have approved modulators for those people with 2 F508del mutations, but not 1. Now, this group we could attack either by doing that single F508del mutation, or the other thing is about 60% of these people on their other mutation make a protein. And we might be able to actually use existing modulators to help them, but we haven't been able to figure that out yet. The last 2 groups are small but important ones. One of these is a 5% who have 2 very rare mutations, at least one of these that makes protein. These are people who could potentially respond to available modulators, but they have rare mutations, ones that we haven't been able to test yet. And then the last group, so Haley, though, as we heard in the video, would be an example of this. She said she had these 2 rare mutations. The last group is this 5% that don't make protein. This is obviously a more challenging group that's going to need other strategies. Now here's the thing that made it particularly challenging as we headed into 2017. 4 groups sounds pretty easy, but this was a lot of variety, and there are over 1,700 different mutations in those 4 groups. So let's think about exactly how much of a challenge that would be. I'm going to give you one little take-home message or take-home fact that highlights some of this challenge with rare mutations going into this year. There are over 1,000 CFTR mutations, which 5 or less people with CF in the world carry. I'm going to say that one more time, just so it sinks in. There's over 1,000 different CFTR mutations, which 5 or less people with CF in the world have. So if we're talking about doing traditional clinical trials, we're in trouble, right? With mutations where there's only 2 or 3 people, that's not going to be possible. So we have to think about other ways of doing this. So if you list these things that we needed to do into 2017, you'd say we need better therapies for those already on modulators, residual function mutations, ability to assess rare mutations, single F508del mutation treatment, class 1 mutation treatment. Well, here's the good news. We made significant progress in every single one of these areas, and actually dramatic progress in some of these areas in 2017. So let's go ahead and dive in to think about what that progress has been. So one of these is better therapies for those already on modulators. So let's start with that group, the 2 F508del mutations that were currently approved for Orkambi. Well, one of the first things that happened in 2017 is we saw the results from the 661-106 trial, which was the result of using tezacaftor, ivacaftor in people with 2 F508del mutations. In many ways, this was asking whether or not Tez-Iva might be a better combination than Orkambi, where they're already approved for. And so this was studied in people with those genotype in 509 individuals, and after 6 months, compared to placebo, that group on Tez-Iva had an absolute FEV1 improvement of 4%, an exacerbation frequency reduced by over 1/3, a quality of life score that improved significantly, and they actually importantly had a similar side effect profile to taking placebo. Now this was a big deal, right? Because remember, 15 to 20% of patients who take Orkambi can get that chest tightness, which makes it hard for them to tolerate that treatment. That was not seen in these trials. The other thing that was a nice thing is that there was less problems with drug interactions with Orkambi because there's less effect on liver metabolism with Tez-Iva. So I think that what we learned from this was really that Tez-Iva is likely an improved or certainly a better tolerated version of lumacaftor, ivacaftor for those with 2 F508del mutations. Now I say that because we have a little bit larger FEV1 effect, a similar effect on exacerbations, a cleaner side effect profile, less drug interactions. Now the FDA is reviewing this, and this is going to be something we're going to have a decision about probably in February of 2018. But I think what we're going to see most likely is this is going to be a new addition to the armamentarium for the most classic type or the most common type of cystic fibrosis. So we talked about some things which improve better therapies now for those already on modulators. Later on, we're going to actually talk about some things which might really improve that for those already on modulators. But let's move on to this next section, this residual function. This was that group that we said we really thought that there was a good chance that they would respond to ivacaftor, but we had insufficient data. There was a decent amount of previous clinical data, there's some laboratory data. Well, basically that started to accumulate. And in May of 2017, the FDA said, guess what? We agree. We actually are approving for an additional 23 missense residual function mutations the use of ivacaftor, Kalydeco, as a monotherapy. This included A455E, the Cali mutation. And then later on this year, they actually said, we've looked some more, and there's actually 5 additional mutations, splice residual function mutations, that we're approving as well. Now, for people like Callie, this was a big deal, right? So she'd been sort of frustrated before. She's in this group that needs a therapy. Well, suddenly this approval made her happy. It also expanded out the number of people eligible to about 13% of our population. So we're talking about 59% of people with CF now eligible by genotype. I should say this is eligible by genotype and in the United States using the CF registry for modulators. There was something, though, that was actually even more exciting, although very exciting for those 28 mutations, but something even more important, I would say, than just those 28 mutations. It was something that the FDA said at the time of the approval. This comes from a press release that was released by the FDA at the time of the approval. I want to read what that said. It said the agency based its decision in part on the results of laboratory testing, which it used in conjunction with evidence from earlier human clinical trials. The approach provides a pathway for adding additional rare mutations of the disease based on laboratory data. So what the FDA did with this is basically open up the door to using in vitro laboratory testing to assess these rare mutations. This gives us a real door, or an open door now, for those 1,000 mutations that we say 5 or less people in the world have. Now, just to show you how much they really meant what they said, let's look at the label. Remember, for the labels, that little box at the top of the drug insert, which tells you how you're supposed to use the drug. And this goes back to the original approval of Kalydeco. The original approval of Kalydeco in 2012 said Kalydeco is approved for anybody with cystic fibrosis who has a G551D mutation, listed the mutation. In 2014, when this was expanded, they said Kalydeco is approved for anybody with G551D, these other gating mutations, and R117H. But look at the label now as of this most recent approval. This now says Kalydeco is for individuals with CF who have one mutation in the CFTR gene that is responsive to ivacaftor based on clinical and or in vitro data. Really featuring this, and they say, take a look at section 12.114. They refer people to it. So let's take a look at that together. This is from sort of further down on that long folding out drug insert. This is section 12.1. And what they do is actually feature the results from laboratory data for Kalydeco using cells. So these are a list of mutations, how much the Kalydeco corrects their chloride transport. You can see on that y-axis. There's a 10% cutoff line, and so everything that's listed here has more than a 10% improvement in chloride transfer, in that this, you can actually have some mutations on there which are even more effective and corrected more than G551D, right, which is the classic. I think another important thing for clinicians is to realize there's also a list of those that don't respond, okay, and this is basically using laboratory data to identify those that would not respond based on laboratory data. There was one other important thing I think to mention. This came from a simultaneously published commentary from Tony Dermowitz, who led the review at the FDA. And what I think he wanted to make clear is a little caveat is that this approach is something to be able to expand the label. And what that means is that you need to be comfortable start off with using clinical trials that a drug works and that it's safe. But after that, once that's been proven, then this approach using laboratory data could be used to start to expand the label to address those rare mutations that we were potentially going to be so frustrated by. So what this FDA decision did is really opened up what I think is a new era of personalized CF medicine, which allows laboratory evaluation of rare CFTR mutations that are unable to be studied in clinical trial. Now this is a big deal, not just for CF but for medicine, because the truth is this had never been done in medicine before except in oncology. The FDA had used oncology a couple times talking about tumors, laboratory testing, but this was the first time in the rest of medicine where laboratory results were used to expand the indication for a drug. Now this use of laboratory data to be able to identify who could respond is called theratyping. Now you're going to hear that word a decent amount the rest of the afternoon. Theratyping is actually just laboratory testing of CFTR mutations using cell lines to determine which available modulators they respond to. Now, for clinicians, this is a little bit different, right? Because we've been sort of taught that we think about mutation classes. And I think in general as clinicians, we tend to say, hey, if you have a class 3, 4, or 5 where the protein's up at the surface, you just need a potentiator, right? And you put a potentiator and those patients will get better. And if you have a class 2 mutation, such as F508del, you need a corrector to get the protein up to the surface and then a potentiator to open it up, such as Orkambi or Tez-Iva. Well, I think the key take-home message here is that this is a good framework for understanding protein biology, but it's really oversimplified when it comes to understanding therapeutic response of mutations. And that's because, unfortunately, the mutation scientific reality is a little more complicated. There's a lot of mutations that have characteristics of more than one class. And as a matter of fact, as we've gotten into this, we realize there's some class 4 mutations that actually don't respond to the current potentiators. One of these would be R347P, which you're going to hear Phil talk about and explain. There's actually some class 5 mutations where we'd say, oh, they just need a potentiator. There's actually growing evidence for some of these class 5 mutations that they could benefit as well from a corrector, which would get more protein up to the surface. And then there's class 2 mutations that don't respond to the current correctors, that are going to need other correctors besides the currently available one to be able to address. So I think the key take-home message is that CF cells, in some ways, with using theratyping simplifies this, right? Because all you do is you use CF cells with that mutation and you say, does this respond to this modulator or combination of modulators? So this is obviously something we're going to be hearing a lot more about, but it does raise a question because we need to be accurate, right? This is going to determine who's going to be able to be responsive to these therapies and become available. We also have a lot of mutations. We've already said that. So how can we do accurate theratyping for so many mutations? Well, anytime that you have a new era, like a new personalized era of medicine, you need new heroes. And so the new heroes in this era are actually going to be our basic scientists, the people who do theratyping, because they're going to actually help figure out for all these rare mutations which of these mutations respond. An example of that would be Dr. Phil Thomas, who we're going to hear from next. You know, I love Phil. He's a great guy, but I have no doubt that when he told people in the past that he worked in a lab with live cells studying CFTR mutations, that what they really thought was this: mad scientist. That was before the FDA decision, however. After the FDA decision, now when he says that he works, Theratype Man, the new superhero. And you know what? It's not just Phil. It's a whole community of basic scientists. So it's Fred Van Goor. Fred leads this effort at Vertex. You know, the modulators that Vertex are developing to be able to go through approval, they're going to have to go through Fred's lab to go to the FDA. But he's leading this effort. Obviously, he's Theratype Man. And then in Europe, Jeff Beekman. Jeff Beekman's leading the same exact effort, looking at these responsive rare mutations and discussing, we'll hear a little bit about that with discussing with European regulators. So, you know, I think we've seen now why the residual function mutations treatment was more than just 28 mutations. It actually opened up this whole new door in this ability to assess rare mutations. I'm going to mention one other thing about residual function mutations that we learned from clinical trials, which I think is an important one this year. And that is that the 661-108 study, which was a study of tezacaftor-ivacaftor in individuals who had one residual function mutation, it's ivacaftor approved on one side, those 28 mutations, and on the other, an F508del mutation. And the question is, would they benefit from not just getting Kalydeco, but would they benefit from getting a combination of Tez-Iva and actually treat both of those alleles? And so they studied 250 patients with this genotype. After 2 months, the group that got Kalydeco alone did improve, an absolute FEV1 improvement of 4.7%, a significant improvement in quality of life. But for people with this genotype who got treated with Tez-Iva, they actually had a significantly larger FEV1 improvement, nearly 7%, and again, a big improvement in quality of life. So I think what this trial told us is that for those with a single ivacaftor-approved residual function mutation on one allele and an F508del mutation on the other, that Tez-Iva is likely more beneficial than ivacaftor alone. Now, the FDA is reviewing this as well. This is something else we'll likely hear about in February, but it sort of highlights how we're going to be continuing to always say, how can we get better? How can we get better with combinations? So we've talked about those first three areas, and I think you can see the progress we made. How about this fourth one, the single F508del mutation? We said this is the biggest one, right? 31% of individuals with CF, and a big part of that group that does not have a current modulator. Now, I will say the things we've already been talking about, therapeutic could make a difference for them, because 60% of this group that have F508del on one allele, on the other allele have a mutation which makes protein and might be responsive to modulators that are available now. We're going to have to do therapeutic and look at that. But wouldn't it be great if we had a therapy that could address that entire 31%? That would be the biggest move of the needle, right? And when we really talk about getting more and more people to be able to be treated. Well, the good news is there's been a lot of progress. And the reason it's good news is we were a little bit frustrated going into this year. Heading into 2017, we said we still have a lot of work to do. Both Orkambi and Tez-Iva had been tested in individuals with a single F508del mutation. And the bottom line is it wasn't good enough. As a matter of fact, in the 661-107 study, was a study of tezacaftor, ivacaftor in individuals with a single F508del mutation and another mutation that doesn't make any protein. And what they found, unfortunately, is after 150 participants enrolled, they looked and they said, hey, you know what, Tez-Iva by itself is not going to be strong enough. We're going to need to have a stronger version, perhaps an additional combination to address that single F508del. Well, the good news in 2017 is though that combination is coming forward. So Vertex has 4 different next-gen molecules which are variations on a theme, 152, 440, 659, 445, which can combine with tezacaftor and ivacaftor to form a 3-drug combination, which appears potentially strong enough to treat even individuals with a single F508del mutation. Now, I've listed other companies up here as well because there are actually several other companies that also have combination therapy which appears highly effective and able to treat single F508del mutations as well. And we look forward to all of those moving forward. Now let's look at some of that laboratory data to see what all the excitement's about. This is looking at a figure, again, using cells, and we're going to start with using cells from somebody who has 2 F508del mutations. We're going to look at the amount of chloride correction or the amount of function correction that they have exposed to a modulator. And we can compare to G551D cells with ivacaftor because we know that that is our bar, our goal that we have, because they have about a 50% correction in the dish, and we know that that results in significant improvement in clinical outcomes as we've seen in patients treated with ivacaftor for G551D. If you use Tez-Iva to treat cells with 2 F508del mutations, you get about a 25% correction. When you add one of these molecules, these next-gen molecules from Vertex, you get dramatically more correction, which exceeds actually the amount of correction you get from G551D and ivacaftor. And this highlights the potential for this being such a big advance and really improving for those people with 2 F508del mutations. How about this one with the single, though? The single F508del mutation, which we said was really our goal, that 31%. This is the exact same figure, now looking at cells with a single F508del mutation. Tez-Iva by itself, about a 15% correction. When you add in a single one of these next-gen molecules to make a 3-drug combination, you suddenly start looking at correction levels that look comparable to G551D cells treated with ivacaftor. Obviously, very exciting data. Now, the question, though, in 2017 would these data translate into clinical, making a difference for people with CF? And the answer is we got the early read on this in August of 2017, and it looks like the answer is yes. So in August, Vertex announced the results of their phase 1 and 2A, these early trials, looking at 3 separate studies of 440, 152, and 659, each about 2 to 4 weeks long. I'm not going to go through each one individually, but I'm going to sort of summarize on average what was seen with taking one of these molecules and adding it to Tez-Iva. And it was really in 2 groups that they looked at. One was in this group with 2 F508del mutations. So in this, the comparison was actually not to placebo, because we already have a treatment for this. The question is, if you have Tez-Iva and you add one of these next-gen molecules as a third one, do you get additional benefits? So that comparison was between Tez-Iva and the 3-drug combination. And the answer is, you absolutely get benefit. There was on average, about a 9% absolute improvement in FEV1, a 30 millimole drop in sweat chloride. Now, how about in the single F508 del? That's our goal. Remember that 31%. This was 61 patients treated. Again, this is sort of an average of these 3 different studies. This was compared to placebo, right? Because we don't have a treatment for these individuals. So the comparison is between the triple and placebo. And again, remarkable results. A 10% absolute improvement in FEV1, a 30 millimole drop in sweat chloride, a 10 CFQR point improvement in quality of life. So I think that's actually worth a clap. That's why I say we're going to look back at 2017 as the time when highly effective next-generation CFTR modulator therapy went from something we were sort of hoping for to now fully expecting to occur. What's next for this, right? Okay, bring it on. What do we got? The next-gen modulator programs, those 3 trials are wrapping up. There's another one that's going on with 445 right now. This is a 4th version of that next-gen. That's moving forward. The results from these 4 trials are basically going to allow selection of the best 1 or 2 candidates. And then those 2 candidates will be moved forward to start pivotal phase 3 studies in mid-2018. The other thing that's actually exciting is there are going to be other companies as well that are also moving forward with combination trials in 2018. This includes AbbVie Galapagos, Proteostasis, Flatley Labs, all have plans for clinical trials using combination therapy in 2018. And this wide variety of some of these molecules makes us more and more confident that we're going to get this and bring it all the way home to be able to get this highly effective therapy. Let's just pause for a second and think about what this will mean for people with CF. So if we are able to come up using this next-gen therapy to be able to treat people with a single F508 del, 2 F508 del mutations, and just the currently approved mutations, nothing else besides that, we'll reach 90% of people with CF with highly effective modulator therapy. And that would mean we would just have 2 groups left. That 5% with those 2 very rare mutations, not F508 del and very rare, but make some protein. And then the 5% who don't make any protein, that we're going to need different strategies. Now, let's talk for a second about that 5% with the 2 rares. That's Haley, right? We talked about her, and she's got 1 or 2 rare mutations and 1 that makes protein. How are we going to go from her feeling frustrated to feeling like, hey, I've got my modulator? Remember, these rare mutations make protein. And so there's a good chunk of them, probably half of this group, of this 5% or more, that's going to be able to be responsive to available modulators. We just haven't figured this out yet because there's so many rare ones. So how are we going to do this? Again, we're going to need our heroes to come to the rescue. That would be whether it's Dr. Thomas, Dr. Fred Van Goor, Dr. Beekman. They're going to be taking on these rare mutations to help us understand in this last 5%. All right? Now, how about this that 5% with the rare? The last 5%, let's talk about them, because obviously this is one that I will tell you the CF Foundation is absolutely committed to developing highly effective therapy for. We're just going to have to use different strategies. Now, what are some of these strategies? There's stop mutation read-through to help patients with stop codons, RNA delivery and repair, DNA delivery and expression, gene editing in stem cells. And just to give you a little bit of glimpse, over the last 2 years, we've actually evaluated over 100 projects in these specific areas and funded 50 of the most promising. We have a partnership with SRI UAB to screen 750,000 compounds to look for new read-through agents to help those individuals with stop mutations. Our own CFFT laboratory in Lexington actually spends more than half of its effort on this last 5%, trying to develop therapies that doesn't matter what your mutation is, including screening 200,000 compounds. And then there's pharma partnerships with Arcturus, Ionis, Recode, 4D Molecular, Sangamo, where we're trying to help them move forward because these are all approaches where it doesn't matter what your mutation is and can certainly help this last 5%. And this is not just a someday thing. This is coming soon. So one of these things in particular would be an example would be RNA delivery. And one of the projects that you'll be hearing about is from Translate Bio. This is delivery of CFTR mRNA and lipid nanoparticles that can be inhaled that reach the cells of the lung that allow expression of CFTR protein, and it doesn't matter what your mutation is. They're planning on being in clinical trials in 2018. So this is, again, not just a someday thing. This is coming soon. And then I'll mention that ProQR also announced that they're going to take the lessons that they learned from their QR010 program in F508del mutations and apply that to mutation-specific repair of common stop mutations, and are planning on moving forward into very early clinical trials in the near future. So as we headed into 2017, we said there was 5 things we needed to do. I'm not going to read through them again. You know them by now. But it's clear that we've made significant progress in each of these and dramatic progress in some of them. So this is why 2017 we're going to look back as such a pivotal year. Going into 2017, we said about half of people with CF needed something better, a little less than half needed something that they needed something. But based on what we've accomplished in 2017, we fully expect that 2020 would look like this. 93% of people with cystic fibrosis with highly effective modulator therapy. You know, and the best thing is it's not going to be just matching medicines with mutations, right? It's going to be matching medicines with people. People like Callie, people like Haley, and thousands of people like them around the world with cystic fibrosis. And then we really will be on our way to transforming cystic fibrosis. So thank you very much for your attention. I'm going to pass the baton now to my partner, Phil Thomas, who's going to talk to us about basic science.
Wow, that's a tough act to follow there, Mike. Thanks very much. And I want to assure everyone that I don't look like that underneath my sport coat. I wish I did, but okay. So this first slide documents my conflicts, and I have a few, and it also serves to document why I feel tired all the time. So I want to thank the organizers for giving me the opportunity and the responsibility to speak here, because I'm representing all the bench scientists, hundreds of bench scientists that have, I'm sorry, I get a little emotional, that have really poured their heart and their effort into this work over decades. And you know, for many years we didn't really see how this was going to result in therapies, but everyone always had that as their goal, that we're doing this work to understand CF so we can get better therapies to people. So this is a huge responsibility to me, and it's pretty stressful to me. It's a pretty good turnout here today. So my wife gave me some really kind of positive advice. As you can see, I'm getting a little emotional. She knows I'm an emotional person. And she said, just, follow your heart and tell people why you have this passion, where we're going to go. That was really helpful to me. And then Professor Boyle, I'm going to call him now, or maybe Michael, maybe that's what his mother called him when he misbehaves. I used to call him Mike, but he's Michael now. He had a little bit more negative. He said, if we don't knock it out of the park after that video, we need new jobs. And I wanted to kind of share what it's like to be a scientist. When I first started working on CF about 1990 or so, people would ask me what I do, and I'd say, I work on cystic fibrosis. And I was so proud, and people were so interested that you're doing something trying to do good for people. But then, Bob, things didn't go so fast, right? 5 years, 10 years, 15 years. And people would say, are you still working on CF? And I honestly felt pretty embarrassed, because when I started, I thought, we're going to do something, and we're going to solve this problem, and we're going to move on and work on something else. So it was a little embarrassing. But after the last couple of years, I have to tell you, I am proud to say I work on CF. So as Michael, or Professor Boyle, told us, at this meeting last year, there were 54% of patients that had access to a modulator that altered the course of their disease. And that's kind of where we're starting. So I want to talk about this remaining 46%, maybe in a little bit more nuts and bolts kind of detail for people. And as you can tell, I'm kind of a homespun kind of guy, so I might tell this in a way you haven't heard before. So let me get my pointer going here. There it is. So as Michael mentioned, in the past year we've got now treatments for people that have residual function, and there's real hope for this 31% with a single F508del mutation. But these are still an unmet need, these rare mutations, and in particular those that when no protein is made. So I just want to show you maybe a way forward, how maybe we can even do better for the people with residual function, how maybe we can actually do better for the people in this 31%, how we can include people in this 5%, and just what the hope for the future is for this remaining 5%. So it's really more about more people, better treatments, and let's get everybody in this group. So there's still a big piece of the pie left, right? So scientists that work in this field, it's all about CFTR, CFTR, CFTR all day long. And in 2017 was really a big year for CFTR too. I know this may not mean a lot to a lot of people, but we had the first high-resolution structure of the full-length CFTR. And this is going to be super useful to improving modulator compounds in drug development programs, better understanding of how this protein really works. But today I'm not going to focus so much on the structure and biophysics and all that, so you don't have to worry about that. I'm going to focus more on how we can bring treatments to everybody by understanding the very simple thing that this protein actually has to do. Okay, and I grew up in western South Dakota, and I work at University of Texas now. So I picked like an example that was a real tangible kind of analogy to me. So CFTR is a gate in a barrier, and it keeps the cattle from moving from one pasture to the other until you open CFTR, and then the cattle can move through the gate, right? So basically all you have to do is unlatch the gate, give some energy to make the gate open, and then the cattle, they're going to go to greener pastures, right? It's quite simple, right? So, but we want to know how fast the cattle can move, or how fast the chloride ions can move, because that's really what CFTR is doing. It's dictating this function of moving something from one place to another. So I'm a scientist, and scientists like equations, so you're going to get an equation, all right? So here's the equation. It looks super complicated because it's got a bunch of letters and Greek symbols and stuff, but it's actually pretty simple. This I stands for current. That's like how fast something moves, how fast the cattle move from one pasture to the other. Now, if you just think about it as a gate, as I showed, it's pretty simple, actually. How fast they move depends on how many gates you have in the fence, right? How wide the gates are, and how many of them are open, right? So N is the number of gates, gamma is how wide the gates are, and PO it's the fraction of time they're open, the fraction of them that are open, right? But in CF, whoops, I pushed the wrong thing. Yeah, how wide they're, okay. In CF, there's a problem. And just as a disclaimer, I want to say that no animals were injured in the making of this slide. So in CF, either the gate doesn't open, it's not wide enough, or it's not even there in the fence, right? And when this happens, there are not enough working gates, the chloride can't move, the airway surface becomes dehydrated, and you can't fight bacterial infections effectively. So mutations can mess this up, this proper process, many different ways. We heard about G551D. Well, G551D, the gates just don't open well. So ivacaftor, what it does is it actually helps the gate open. It helps you open the gate. Delta F508, there's no N. The gates aren't in the barrier. They're not even there to open. So you need a corrector to help you get that into the barrier. luckily, thanks to the work of Vertex and other companies, we do have an armory. We have an armory. The first thing in the armory is Kalydeco or ivacaftor. And now you all understand this equation so very well. Ivacaftor opens the gate. It makes PO get bigger, right? Okay, but we also have other things. We have Orkambi, which is a combination of ivacaftor, which makes more of the gates open, but it also increases the number of gates that are in the fence, right? So it acts on two of these things. But you can see, if you remember your simple mathematics or arithmetic, if you multiply bigger numbers together, you get an even bigger number, right? So if you double N and you double PO, you're going to get 4 times as much I, right? So this is a good thing, right? But unfortunately, there's other mutations. This would be a so-called class 4 mutation, such as R347P. Here the gate, even if it's open and it's in the membrane, it's not wide enough to let a longhorn get through, right? And unfortunately, we don't have any modulators to attack this right now. So these people that have these kinds of mutations, they're kind of in the same boat as the last 5%. They make protein, but it's protein that's going to be, we don't currently know how to repair, all right? So Mike discussed the class system and how that was really useful for doing mechanistic studies and understanding what these mutations did to the protein to make it defective. I think this is actually a simpler way to think about it. How fast can we move the cattle? I know they're cattle, they're not cows. Cattle from one pasture to the other. And it really depends on getting the gates to where they need to be, getting them open the right amount of time, and making sure they're wide enough to let the chloride move through. And so one way to do that, you know, as a farm boy, you fix everything with, you know, baling wire and duct tape and spit and glue and stuff. You just like open your eyes and look at what happens. And that's really what everyone's been talking about today. We're going to just start mixing things together and we're going to look and see what happens. That's really all it is. So, sorry, I have too many buttons to push here. And so this is what we're calling therotyping. It sounds very fancy, but it's actually pretty simple, right? Therotyping, it's so important, there's actually a Latin and a Greek root of the word thera, and it leads to healing. It means healing, some way to heal, therapy, healing. Type just means a group or a bunch, a group of things of a similar kind. So all we're saying is we're looking for a group that responds to a similar type of healing in the same way. It's a group that responds to a healing treatment. Sorry, I'm speaking faster than I'm turning my notes. Okay, one fact Michael didn't give you, he talked about that there's 1,000 mutations that there's only 5 people with, but it's actually really a more profound problem now when you think about it. 33% of people that suffer from CF in the US have a mutation that there's only maybe 50 other people or less that have that mutation. So those are small numbers. So what we're going to talk about next is the premise that many of those rare mutations may respond to these armaments we already have in hand, these drugs we already have that are approved. So that's a simple premise. We're going to just look and see which ones do. And key to this effort is knowing what the mutations are, and I just want to give a shout out to Gary Cutting and the CFTR2 group. I don't see Gary here, but I'm sure he'll correct me after the talk if I say anything wrong. But they have identified all of these mutations, and they have determined which ones are actually causing disease and are not just kind of red herrings. So that's basically foundational to everything that's being done. And here's a picture of Gary. Oh, Chris, they changed your picture. Okay. So this is really important work. So it's important to know what the mutations are, and it's also, because these mutations are so rare, we may not have access to all kinds of systems that we do for the more common mutations. So the other thing that's really clear, if we're going to use cell-based data to try and do this is it has to show a correlation. In other words, what happens in the cell has to predict or tell us what's going to happen in the patient. Like if we see this in the cell, are we going to get a clinical benefit? And this slide very importantly shows that. And here on the bottom, this is just a scale showing the activity of CFTR. It could be I, right, in a cell. And these are actually human bronchial epithelial cells that are isolated from lung transplants, lungs that are removed during the transplant process. And then you can see there's different variants of CFTR, different mutations here, and there's their responsiveness to a drug. For instance, here's G551D with ivacaftor. You can see you get a lot of activity in these cells, and that predicts and correlates with a lot of improvement in lung function. So this is critical that the cell work tells us what's going to happen in the patient. Otherwise, this is all just a misspent effort. Okay. So if we can use cell lines, we can actually do this kind of work much more quickly than having to isolate, do a clinical trial, for instance. So, but the other thing is we don't always have these human bronchial epithelial cells or a lung transplant from patients with these rare mutations. We certainly don't have them much more rare, less commonly from people that have residual function mutations because they tend to be healthier, right? So we want to use cell models, real cell models. And we want to do something, as you can see here, this is in the CFFT labs in Lexington. It's a robot that's making these measurements. And we want something that can do this measurement very quickly, precisely, and accurately, and reproducibly. And we're measuring I. So again, Vertex shows the way forward. Okay, I'm going to walk you guys through this. I know this looks complicated. So what Fred and his group did is they evaluated 54 different CF-causing mutations in a cell line, an animal cell line. And the height of this black bar tells you how much function you have with no treatment. So some of these actually aren't CF-causing, but you can see some of these have quite a lot of function, and then it drops off to almost nothing. But when you treat with ivacaftor, right, you get the white bar. And you can see many of these, there's hardly anything before. And then the bar gets quite long after the ivacaftor. So I just glanced at this, even though I did know the answer at the end. I just glanced at it and I said, well, if I was a pessimist, I might say, okay, these are the ones I'm going to go for. If I'm an optimist, I'm going to go down here and get everything. But I'm kind of in between, so I draw a box like that. So these all look like, boy, there's a fairly good response to ivacaftor. Cell lines. Those are the mutations that the FDA approved for the label extension based on this data. And in here somewhere, I know it's small to see, but the Haley's mutation is in here, right here, A455E. And you can see, got a little bit of residual function. She gets about twice as much after the ivacaftor. Okay. So let's think about that for a second. So she's getting some benefit, clearly. Callie, I said Haley. Callie. She's got the A455E. She's in this group. She's got some improvement on ivacaftor, and she's approved for it. But actually, there's maybe more to be gained here, right? So there, this is great, but maybe it's actually could be even better, right? So here we go. Here's the data, again, courtesy Fred Van Gore, Vertex. Here's the function of that mutation in these animal cells without treatment. With ivacaftor, you can see you get a bump. There's definitely more. But I have to tell you something. You know about the gate and the equation now, right? A455E actually has a bigger effect on N, the number of gates that are in the fence. So what do you think would happen if we put a corrector on there that raises N? And now we have more N. Remember, N now bigger, and we can multiply by the effect we had on P. We get even more effect. So here you go. You add tezacaftor, even bigger effect than ivacaftor alone, and the two together, this is really something we would predict would make a huge, huge difference in people with this mutation. So the cell model says, yes, we're going to know soon, all right? Because Vertex is conducting a study in Holland that's a combination of lumacaftor and ivacaftor on patients who have a A455E mutation. There's 20 participants, ages 12 and above. They're going to be treated for 2 months, and we're going to know the results very, very soon. But my expectation is, based on my belief in the cell models, is that this is going to be a happy outcome of this trial. Okay, so what about these other people that have really rare mutations? Whoops. Such as Haley. As Michael mentioned, these patients, you really can't do a clinical trial on them because the numbers are so small. But some of these actually could be added to the label extension, because I mentioned I don't know what the number is Vertex has done now. They did 54 originally, but some of these patients, we may have to look at hundreds and hundreds and hundreds, but there may be some people way down there in the rare mutations that could really benefit. So how are we going to do this? How are we going to try and expedite this? So we're going to do 2 projects, right? The first project is serotyping of these rare mutations. So we're going to use the foundation supporting an effort to test almost 650 rare mutations. And these are mutations that make protein. They're all make a single mistake at one amino acid position, or they cut a little bit out of the protein, but they make protein, okay? So we're going to look at the 649 mutations, and we're going to do this at 3 different sites, including the CFFT labs run by Martin Mensa in Lexington, my own lab, and Bob Bridges' lab in Chicago. And here's pictures of the people that are going to be doing the work. And the key is they're going to measure I. They're going to measure how fast the chloride moves from one pasture to the other. And Bob has developed a very simple but reproducible and accurate method to measure something related to I. And we can do this very quickly, very, very quickly. And if you look at the last slide, I think we're at the point where we can do 30 of these rare mutations every week at each one of those 3 sites. So 650 sounds like a lot, but at 30 a week, we can move through these pretty quickly. I anticipate we'll have all this data sometime in the first half of next year. Okay. And the other thing I want to talk to the last 5% of people, don't think again you're getting left behind. I know I'm not supposed to say that, because you're not. This same kind of approach, I'm going to show you in just a few slides, we can use for people that have nonsense mutations that don't make protein, right? Okay. So this just gives you a taste of the kind of data we're getting. I anonymized this so you can't see what the mutations are, and there are reasons for that, because we don't want to reveal them even to the people doing the experiments until the end of the study. But this is just a small group, and here's a normal CFTR in this system. And you can see, unfortunately, there's a lot of mutations. The white, no treatment, green with treatment. There's quite a few of them that don't respond, but encouragingly, there's a large number that do respond. For instance, you can look at this particular one. There's very little function, and you add lumacaftor and ivacaftor, you get quite a lot. Quite a lot. Many of these would definitely benefit from these treatments. So it's not going to be a rare thing that just a few of these people with these mutations benefit. I think there's going to be a significant fraction of the people, and time will tell. We'll know quite soon. Okay. This is to the scientists, because we have to be careful with this, because we've been handed a golden opportunity, and we have to treat this with kid gloves. We have to do this right. We can't mess this up, right? So that means we have to get the right answer. We have to get it right. And so just for the general audience, a false negative means you get a result that says that modulator doesn't work for that mutation. That's bad. right? Because that patient could benefit from that if that's not a true result. So we don't want that to happen. But false positives are bad too. That means we say, oh, that patient's going to benefit from that. Because if you get too many of those, it's going to cast doubt on the whole enterprise. So we have to do this very carefully, and that's what I mean by rigor, and that's why I said we blind these studies. The people making the measurements don't know what they're working on. We're doing this at multiple expert sites with really standard protocols, and there's internal validation. I've doped in wild type delta F, G551D all over the place on these samples people are getting, and they don't know where they are, right? So this is really important. And if you want more clarity about this, you could look at this Drumovitz. This is actually the publication that Mike talked about, of the article Mike talked about. It just came out October 17th, just a few weeks ago. So you can read this, particularly the scientists, to see why it's important to get it right. So in the last few minutes that I have, I'm going to turn to a different kind of therapy. So what I've showed you has already been very successfully exploited by Vertex to bring more people onto the label for ivacaftor. And hopefully this is going to lead to many, many more people getting benefit from these modulators that are already on the market. But you know, sometimes it can be more complicated because we all aren't just made by the CF mutation that we have that causes CF, right? We're all individuals. We all have lots of changes in our DNA. And these things, that's what makes us, but it also can complicate things, how we respond to drugs and things like that. So this is a case where maybe you really want to go directly to a person's own cells, samples from a person. That's truly personalized medicine. So there's 3 ways where this is already happening. And you saw Professor Beekman in his Superman costume earlier, and I'm going to tell you a little bit about the data that put him in the Superman costume. But he's using cells isolated from the intestinal tract of a patient, and they make what are called organoids out of those, and those can be used to test the responsiveness of CFTR to modulators from an individual person. There's also several other labs working along these lines in UNC, Cincinnati, Alabama, Chicago, etc. Another way is nasal cells, cells that are removed from a brushing of a patient's own nasal cavity. And these cells can be isolated and grown and be used then to measure CFTR function. I'm going to show an example from Case Western Reserve, but this work's also being carried out at many different sites supported by the foundation. And I'm not going to have time to talk about this today, but a third way is you can collect cells from a patient's blood that are called adult pluripotent stem cells. And people such as Jed Mahoney at CFFT Labs in Lexington, Brian Davies, etc., there's many groups working on this. You can add certain cocktails of compounds to these, and you can get these iPSCs to differentiate into lung cells. So they'll have the same genome as the patient, but now they're lung cells, right? And those can then be used for direct testing in the context of the person's own genome. So organoids. So these are basically a group of cells that make a little balloon it's a sac. It's got fluid in the middle of it. And you can see if you add something that activates CFTR and induces fluid secretion, it should blow up, just like blowing into a balloon. It should blow up, fill up with fluid. And you can see here for delta F cell patient organoids isolated from such a patient, they don't really do much. But if you put them on lumacaftor and ivacaftor, you can see, right? So, I mean, you know, I'm a molecular biologist, so I'm not used to seeing anything. I mean, this is really exciting to me to see something move. So thank you for that, Jeff Beekman and his group. But even more importantly than being able to see this and make a cool picture, is it underlines what I was saying before about the data generated by that model predicts the clinical outcome of the patients. And again, there's a number of different mutations on here with different therapies, and they look like they're all scattered, but what I want to see is there is a trend here where if you don't get swelling of the organoids, you don't get any improvement in lung function through FEV1. But these that get the most organoid swelling, you also get, those patients get the most benefit from that treatment. So this is really a remarkable thing that, again, these cell models can predict what's going to happen in a patient, and it opens a new door to use them to bring more patients into the treatment class. Oops. So these Europeans are quite clever, you know, and they are building on this data and their success with these organoids to do something that's really even more remarkable than what we talked about today. And this is to try and use this kind of model to design a trial so you can actually do a trial with patients with rare mutations and get approval, not simple label extension of something that's already approved. So the aims of this study are to validate the organoid assay, and you can see some of the work in the prior slide certainly does that, and use this as a path for drug approval in patients with mutations. This is called HIT, CFTR. Even the Dutch can't tell me what this is an acronym for. So, but anyway, the plan, and this effort's led by Cors van der Ent in Utrecht, is to standardize the assay, recruit patients that will donate these samples, in particular those with these rare mutations, and test CFTR modulators, not the approved ones, but ones in development on these organoids, and then pick some of the ones that respond and some of the ones that don't respond, and use that to design a trial so you kind of have internal controls rather than the trial. And the hope is with this robust data set, you can discuss with the European regulators and actually get approval. So this would really be the next step forward. So let me tell you a little about the nasal cells. And this was done by Cal Cotton at Case Western. And I've not shown you what the mutation is, but there's a patient in here with a rare mutation. And I just want to show you, nasal cells were isolated, and the black solid line here is delta F, and you don't really need to understand what all these lines mean. Just realize the bigger the bump, the better. The more I there is, the more gates that are open in the fence. So here's delta F, and here's delta F treated with lumacaftor, and actually lumacaftor and ivacaftor. And you can see there's certainly improvement. Now here's the rare mutation, this black dashed line. So they have a bit more than delta F to begin with, but now you put lumacaftor on here, this thing just goes through the roof, right? So this patient's not on a therapy now, but Cal said, oh gee, I wonder what happens in your cell lines. So we actually introduced the same mutation into the cell lines we're using for therapying. You can see here, here's the normal, here's delta F without treatment, and here's with lumacaftor. You can see more. Here's this rare mutation without treatment. It's down there, right down there with delta F508. You treat it with lumacaftor, it's up to almost normal levels. So one would predict that that patient would get profound benefit from treatment with the lumacaftor-ivacaftor combination. Okay, the last 5%. What did I do here? Oh, I moved something. The last 5% here. So this is the people that don't make any protein, nonsense mutations, etc. I mentioned earlier that we would like to do a therapying effort on these patients, but right now we don't have modulators. These screens are going on. Hopefully something's going to come out of the screen that's going to allow read-through, etc. But once we have that, we want to do therapying on these as well. And this is data that comes out of the CFFT labs, and it's from Hillary and Jerome. And I picked to show this for two reasons, right? So what they've done is they've taken human airway cells that actually Dieter Gruner, rest his soul, produced about 20 years ago, and these were normal human airway cells. And what Hillary and Jerome have done is, in this case, they've introduced delta F508 into this cell line. So they've, this is not what you normally want to do, turn a normal into a mutant, but this is what we want to do for therapying. And they did it using this gene editing technology. So while we're doing this, making these models, we're learning more about gene editing as well and how we might do this in the opposite direction in the future. But I just want to show you, here's the normal function of these cells, here's the delta F. You can see there's not much of a bump, but you add lumacaftor on here, you see you get the bump. But more importantly, this has now been done for these nonsense mutations. We've done 2 of them already, there's 3 others on the docket. We'll have all these in a number of months. And this is important because the models I showed you before, it's not relevant to put the nonsense mutations in those models. It is relevant to put them in these models. So this is a very useful, relevant model to study the patients that have these last 5%. Okay. So I think, there's been spectacular progress. The ladies that were helping me with my slides say, you've got remarkable 5 times on that same slide, right? But it has been remarkable. It really has been remarkable. And the future is bright. So we're working for new modulators for nonsense mutations. Michael told you about mRNA therapy that is mutation agnostic, but would require repeat administrations. But finally, the hope of all of us is that the gene editing can be really brought to bear eventually on the problem, and we can just one and done, be done, get the cattle into the right pasture, go sit on the porch, right? So that's my goal. So I just want to finish here with a couple of things. I hope I've conveyed the importance of the bench science. It may not have seemed 20 years ago that it was really making a difference, but a lot of the work that we showed you here today in this progress is based on things that were done a long time ago. It just takes a long time to bring this to fruition. I was talking to Bill. We've really reached the tipping point where all the work that Bob and his group early funded that explained how the protein worked, how it gated, how it got to the membrane, etc. Now this is all being brought to bear along in combination with these molecules. It's a really tipping point. We're going from 5% treated to 90% treated over a matter of years. It's just remarkable. So based on this knowledge, I think the future's bright, and I'm proud to say that I work on CF. So I thank you for your attention, and please enjoy the rest of the meeting.